Hi there, folks. Today we're talking about medians and altitudes. And we're going to look at this inside of a triangle. Once again, we're going to draw all the medians, see what the relationship is. We'll draw all of the altitudes, see what the relationship is. And then investigate all the kind of special properties that emerge from those relationships. And so the first thing we got to look at is a median. A median itself basically goes from the vertex to the midpoint of the opposite side. So it's a segment whose endpoints are a vertex and the midpoint of the opposite side. So we just go from, vertex from one of the points on the triangle, and we just travel to the midpoint of the opposite side. That's a median, all right? And when we draw all the medians, we get a point that is, once again, we get a point of concurrence where they all intersect at the same spot, and we call that thing the centroid, okay? So a median connects the vertex to the midpoint of the opposite side. If I draw all of the medians, they come together at the centroid inside the triangle, okay? And the centroid is the point of intersection of the medians, but it's special because when we measure, and the way this is stated, we can think of this a bunch of different ways, but this is how it's going to be stated in terms of the medians, all right? If we look at this theorem down here, the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint, all right? And, that's probably the worst way for students to think about it as they're trying to solve problems. It's the way that it's stated, but we can think about it in a bunch of other ways. So 2/3 the distance, but that's when you're measuring from the vertex to the midpoint. In other words, when we look at this thing, here's the centroid right here. It's basically saying that, hey, if I measure from the vertex to the centroid, this right here is 2/3 of the distance of this entire thing, okay? So as we break it down, if I knew the entire thing of this was 15, I would know that this piece right here would be 10, okay? It's 2/3 of the distance, all right? And we can find values by multiplying by 2/3 and that kind of stuff, all right? So that's just the way that it's stated. We can think about this in a couple different ways, all right? And we'll write these down underneath here at some point. But when you kind of think about this, if it's 2/3 the distance, I'll use that same centroid, median. If I looked at this same guy, if this is 2/3 of the distance, what would the little piece be compared to the whole thing? All right. If one piece is 2/3, well, this would be 1/3. All right. And you can think of it that way. All right. If you're measuring from the centroid to that midpoint, that's 1/3 the distance of the overall length. Okay. And now the real interesting thing here is instead of comparing it to the whole thing, so it's 2/3 the whole thing. So that larger piece is 2/3 of the entire median. All right. The smaller piece is 1/3 of the entire median. But let's compare the big piece and the little piece. And the idea of how they compare, if this piece is 1/3 and this piece is 2/3, you see that this piece is twice as much as this guy. In other words, we could think of it if we kind of compare these, and I'll use some x values here. But if I thought about this as x, this would just be 2x, okay? The bigger portion is twice the size of the smaller portion, all right? Or you can think of it as the smaller portion is half of the bigger portion, okay? So when we talk about that 2/3, 1/3 split, we're comparing it to the entire median. We're comparing it to the whole thing when we compare that 2/3, 1/3 split. Okay? And so if you kind of look at the way I have this drawn right now, the whole thing, if I add it up, would be 3x. And so can you see that right here, x over 3x, that would be 1/3, okay? 2x over 3x would be 2/3 of the whole thing. And so we can kind of think of it in a couple different ways here, and I think it's really beneficial to think of it a couple different ways. This right here, what I have drawn, I think this is the easiest way for students to think about the centroid. Okay? I think it's the easiest one to comprehend and to be able to find the values. Okay? So let me jump down here. Let's kind of summarize that for a second. Okay? So let me summarize the theorem here first. The 2/3, all right, that's the larger portion. So I'm going to call it the big piece and the little piece, all right, to make it really easy. The big piece, all right, is 2/3 the whole thing. All right? But then we could also think of it this way. We could say, hey, the little piece is 1/3 the whole thing. All right, that's one way to think about it, kind of looking at it. And the reason the 1/3 is easier, because then you're just dividing by 3. If you have the whole thing, divide it by 3, you got the little piece. And then you can use this kind of technique. If you kind of look at it this way, we could say, hey, the big piece is 2 times the little piece. Likewise, the little piece is half the big piece. Okay? And so if we think about it that way, it makes it a lot easier. Sorry, I capitalized a big and little the whole time, so I got to keep it capitalized. Why not? But when we think about it that way, it makes it a lot easier. All right? And the one that I tend to shy away from, and the one that students find the most difficult, is the one, the way it's written, the 2/3 thing, and the way it's defined in the textbook. It's a lot easier to think about it this way, okay? To say, hey, the little piece is 1/3 the whole thing. It's divided by 3, okay? And then if you understand that, if you can get the little piece from the whole thing by dividing by 3, well, now you look at the relationship between the big piece and little piece. You say, hey, the big piece is 2 times that little piece, okay? And that's it. All right, so it's really easy to kind of jump around. If you start with the big piece, you say, oh, the little piece is half of that thing, all right? And then the little piece, you could multiply by 3 to get the whole thing, all right? It's just kind of working backwards. And so that idea of kind of splitting it up more in terms of like, hey, if this is x, 2x, and then the whole thing would be 3x, and kind of thinking of it that way. You could even set it up that way and think about it in terms of proportions, okay? For example, let's take a look at something like this guy, all right? Just kind of jumping around this thing, all right? So given AD is 18, so AD is 18, GF is 4, BG is 14. I want to find each value, okay? And so right away, I am looking for AG first. So this is the first thing I'm looking for is this guy right here, okay? This piece, AG. And so I have to look at what that's part of. Notice it gave me AD is 18. And so if I think about this the easiest way possible, the little piece is really easy to get. It's 1/3, right? So it's divided by 3. 18 divided by 3 is a 6. So this little piece right here, GD, that's 6 units. And then AG is twice that. So that's going to be 12 units, okay? That, I think, is the easiest way to think about it, okay? Yes, I could just say that, hey, AG, the big piece, is 2/3 the whole thing, and do 18 times 2/3, that will also give me the 12. It gives me the same thing, all right? But thinking about this from a mental math perspective, most students find it easier to remember, hey, divided by 3 for the little piece, okay? It's 1/3 of the thing. That's easier to remember, okay? And then the other guy is twice the size, okay? The big piece is twice the little piece, okay? And then we can work backwards to kind of figure out those other pieces, okay? The next one, CG. Let me erase what I've put over here so far. So CG this time I want to find. Once again, that's that bigger piece. But notice it gives me the little piece this time. Okay, so it gives me that smaller piece, GF. It tells me this is 4. And so if I'm thinking about it from that perspective of, hey, the big piece is twice the size of the little piece, well, CG is easy to find now. That's 8. Okay, and notice we have that. If you look at the whole thing, it's 12. That gives us that 1/3, 2/3 split. Okay, if the whole thing is 12, 4 over 12 is 1/3. That's the little piece. Okay, 8 over 12 is 2/3. That's the big piece. Okay, so right here, 8. But again, I like to think of it this way. Kind of run it through that little piece. That's an easy one to find. That's an easy one to think about. Okay. The next one, FC this time. So FC is this whole thing. And I just erased that stuff. Let me see if I can undo it. Okay, so FC is that whole thing. We already talked about that. That whole thing is 12. We already have that answer just from discussing what we've done previously. Okay, and so if the big piece was 8 and the little piece was 4, the whole thing is 12. Okay, and so I kind of scoop up all these pieces as I work through and find the little piece, the big piece, and then I can find the whole thing. Okay. EB this time. EB, I'm looking for the whole thing. So think about how we just got the whole thing in the previous one. All right. I went through and found those pieces individually and then found the whole thing. So this time it says EB. I want this whole thing over here, but it tells me BG. So it says BG right here. This is 14. So if the big piece is 14, what's the little piece is the question. okay? And here's the thing, you know that the big piece is twice the little piece, so the little piece has to be a 7, all right? And notice, I'm really only talking about this from the perspective of two of these things up here. I'm basically using this guy, the 1/3, and this guy, all right? This other thing kind of happens automatically, but if I just remember, hey, the little piece is 1/3 the whole thing, the big piece is twice the little piece, makes this really easy, okay? So in this one, the big piece is 14, the little piece has to be 7. And so now the whole thing, well, that's got to be a 21. I can use my segment addition postulate for that, okay? And again, you could work through and say, hey, you know that 14 is 2/3 the whole thing, so I could set up an equation like, hey, 2/3 times the whole thing equals something like 14, and then I could divide each side by 2/3 or multiply each side by 3/2, that kind of thing, okay? Again, I think the easiest route to go is we think about the little piece is 1/3 the whole thing, so it's divided by 3. The little piece is, the big piece is twice the little piece, okay? That's the centroid. It gives us that 2/3, 1/3 split, and hopefully we can see it here. That whole thing that I just, EB is 21. The little piece, 7 out of 21 is 1/3. So this is 1/3, okay, right here. 14 out of 21, that's 2/3. So we see that split. We just think about it in a different way, okay? Okay, so the little piece is 1/3 the whole thing, so divide by 3 to get it. The big piece is twice the little piece, okay? If I look at this one, given two medians, find the value of x and y. So it's telling us that these are medians, all right? So it's telling us right away that these are medians. In other words, this guy is congruent to this guy. These pieces right here are congruent, all right, because I'm going to the midpoints, from the vertex to the midpoint of the opposite side. But now I have to think about, all right, what information do I know when I kind of look at this thing? And so as I kind of look through here, if this is a median, again, it's that 2/3, 1/3 split, when I look at the big piece compared to the little piece here, well, we know that the big piece is twice the little piece. So it's really easy to look at this and say, hey, you know what? My y value has to be half the big piece then. So that's got to be an 8.5. That's it. I just divide the 17 by 2, all right? If I know that the big piece is twice the little piece, it's really easy to find that by dividing by 2. Okay, and so it simplifies this down to essentially multiplying divided by 2 or multiplying divided by 3. Okay, if you remember it as the little piece is 1/3 the whole thing, the big piece is twice the little piece. Okay, likewise, if I look at the other guy here, again, if I compare the little piece and the big piece, so here's the little piece, there's the big piece. Well, we know that the big piece is twice the little piece, all right? So I already know what the big piece equals. If I ignore that 2x minus 4, that big piece is 20 units, all right? It's got to be a 20. Well, now I have an equation to solve. 2x minus 4 equals a 20. I add the 4 to each side. I divide by the 2. Whoops, I missed the 2 in my 24. Hilarious. So now I have my x value. Okay, not too bad. And again, it's still that 2/3, 1/3 split, but it's easier to think about it as, hey, the big piece is twice the little piece. And when we have the centroid and we have that medium split, all right, that median split, the small piece and the big piece, what's the relationship? The big piece is twice the small piece, all right? The little piece is 1/3 the whole thing, okay? Let's talk about the altitude. So the altitude of a triangle is basically just a perpendicular segment that goes from the vertex to the opposite side. And so both of these are kind of in the same vein. You know, when you think about a median, it's going from the vertex to the midpoint of the opposite side. This one's going from the vertex perpendicular to the opposite side. It's essentially measuring the distance across the triangle, okay, from each vertex. And so, again, the idea behind measuring was you always measure the shortest distance possible. We always measure at a perpendicular line. That's the altitude, okay? When I measure the distance across the triangle, I'm essentially drawing an altitude. I'm going from the vertex perpendicular to the opposite side, okay? And when we do that, those 3 points intersect at a single point, and we call that single point the orthocenter, okay? So that's the orthocenter. That's the point where these guys intersect, okay? And so when we look at this thing, again, if I were to kind of draw this, that's perpendicular. So I went from this vertex perpendicular to the opposite side. Over here, I went from this vertex perpendicular to the opposite side. What you have to do here, and sometimes this happens with the orthocenter with altitudes, it's you have to extend each of these sides, okay? See, I can't draw from here and hit this line anywhere in here, you know what I mean, and be perpendicular. It's not possible. In order to be perpendicular to that line, I have to extend that line segment, okay, into a line. And see, if I extend that side, if I extend this guy out, which I've drawn it out here, okay, if I kind of extend this line out here, okay, now I can go from this vertex and be perpendicular to that side, okay? So sometimes I do have to extend the side, and I had to do it here too. Ready? If I look at this guy, I had to extend this side right here, this base side. I have to extend it out so that I can draw a line that's from this vertex and that's perpendicular to this guy, okay? Altitudes become very important because they're our way of measuring the distance across the triangle, okay? Or measuring the height of the triangle. Like if I wanted to know how tall is this triangle, I would measure from this vertex straight down to the ground, okay? So this measurement over here, this altitude would measure how tall this triangle is if we're looking at this guy down here as the base of the triangle, okay? That's what altitudes typically are used for. That's where they really come into play, is that idea of measuring the height or measuring the distance across the triangle, okay? And so the orthocenter comes together at these 3 points. And so let's talk about what's special about that. Absolutely nothing, okay? We spend all this time talking about the orthocenter here for a moment. The orthocenter is where the altitudes intersect. What's special about it is that they intersect at one point. And that's pretty neat. It's pretty neat that they all come together at one point, but there's no special properties here in terms of some other thing that they give us, okay? Unlike some of the other things we had, like the circumcenter and the incenter and the centroid, they all had other special properties. You know, the circumcenter was the same distance to all the vertices, all right? The incenter was the same distance to all the sides of the triangle, all right? The centroid, you know, we had that 1/3, 2/3 split, okay? And now the orthocenter, there's nothing special other than the fact that, they meet at a point, and that's kind of neat, all right? It's neat that happens. All right, let's move on, all right? So if I look at something like this guy, the coordinates of triangle ABC, so let's plot these. I've got A at -4, 4. I've got B at -6, -2. I've got C at 2, 2. And so I can draw this triangle. So I'm trying to draw it accurately. There we go. So I've drawn the triangle. I want to find the orthocenter. I might have to estimate here depending on where it is. But I just have to use the vertex of one side and go perpendicular to the opposite side. Okay? And so the idea here, like if I started at this guy right here, if I started, I guess I should label these A, B, and C. If I start at A, I want to go perpendicular to the opposite side. So I want to be perpendicular to BC. I have to consider the slope of BC. So if I talk about the slope of BC, the slope of that is up 1/2, up 1/2. That has a slope of 1/2. If I want to be perpendicular to that, I need a slope of -2. Remember, opposite reciprocal, okay? So I'm starting at point A, but to be perpendicular to BC, I have to start at point A and use a slope of -2, okay? And so let me plot this. Ready? I start here, slope of -2, down 2/1, down 2/1, down 2/1. Okay? That would be my altitude right here. I've drawn a perpendicular line to the opposite side. Okay? And now I want to do the same thing from each of the other points. So maybe I go to point B next. So if I'm starting at point B, I have to be perpendicular, all right, to AC. So once again, I got to look at the slope of AC. Let me write it off to the side here. The slope of AC is a -1/3. So to be perpendicular to that, I have to have a slope of +3, opposite reciprocal. So I'm starting at B with a slope of 3. Let's see. That's up 1/3, up 1/3, up 1/3. Look, it's this side of the triangle. Is it okay for the altitude to be one of the sides of the triangle? Well, yeah, it just means that, hey, this guy right here, this was a right angle all along, okay? Let me extend this other guy. All right. So I've got two of the altitudes drawn. I really don't need to draw a third altitude. All right. I know that it's also going to intersect at the same point, and we can see where it's intersecting. It's literally intersecting at point A, but let's confirm it. You ready? This time I want to start at C. If I'm at C, I want to be perpendicular to AB. All right. So AB has a slope of 3. That's 3 over 1. So if I want to start at C and be perpendicular to that, I need a slope of negative 1/3. So from C, a slope of negative 1/3 is down 1 over 3, or up 1 back 3, up 1 back 3, up 1 back 3. And you see, we already kind of knew this was going to happen, but this just confirms it, okay? And so once again, I can see where all three of those come together. The altitudes, yeah, two of the sides were actual altitudes, and that's okay. Sometimes the sides are altitudes, okay? If they're perpendicular to the opposite side, well, then yeah, that happens, okay? Just means this is a right triangle, all right? And so the orthocenter here is where all three of those altitudes meet up. And for this one, that's the order pair negative 4, 4. Okay? There's nothing else that's really special about it other than the fact that, yeah, altitudes themselves will become important, but the orthocenter really doesn't give us anything else. It's neat that they all come together. Okay? The big takeaway here was the centroid. The centroid has some special properties. It's got that 1/3, 2/3 split. Okay? However you decide to remember that, again, I think the easiest is the little piece is 1/3 the whole thing. The big piece is twice the little piece. Okay?